Okay, now it's we'll get back. I hope in the first hour I didn't upset you and so with a lot of equation or it's boring you with without much of detail. But I hope you just get it's a very very general form what's a Bayesian network and what you need to construct is a Bayesian network. Here it's going to get a little bit into detail what happened biological data, how we can using this data to construct more in some sense a biological network. So I would say this one is from Stephen Friend. He is I don't know where he got this picture. This one is really nice. It really capture what we want to do. What association was is causality. So that's one is the next hour we're always focusing on the causality, but why we need focus on that. So here is one. So his doctor told him that fat dog and correlate the fat master. Then he construct a plan to see how to deal his obesity problem, just like the dog run on the treadmill. So definitely there's a correlation, but will this correlation give you the causality? That's the question. So in biology, that we know that a lot of things is correlated, and question is can we derive it's a causal relationship from here? Let's say it's starting with 3 nodes, they're all correlated. Do we have all this causal structure that we just showed before? Then with some of the Bayesian networks, some of maybe don't. But can you see which one is the causal structure fit your data best? Right, that's just a general question. If you want from the association called to really is the causality. So then basic approach is that we just talked about is when you have 3 nodes, they have a data, then we can enumerate all the possible structure and find what is the best is a model to feed this data. Simple, but actually it's not that simple. So you can see here, this one is the best model, but this one is look here, the edge is different. This one edge is different, but they're equivalent. So they're called as a Markov equivalent. What they mean is mathematically, they're exactly same as the same form. So mathematically, they're equivalent. Well, what that means is the Markov equivalent is this structure. If you look at A, B, C, the relationship capture exactly the same relationship. What the relationship is conditional on A, B, and C. They're independent. So there is a probability give you exactly the same form. Mathematically given data, there's no way you can distinguish these 3 structures. So that where get is a big problem. You want to get causal structure, you may get causal structure, but actually they're not causal because you cannot distinguish all these edges. Still end up the same as an undirected graph. So the question is that if you want to say that so general will get here. This Bayesian network, even though they are directed graph, but that directed graph doesn't mean it's a causal graph. So even though everything is a direction, but that direction doesn't mean it's a causal because everything is just fit model. So how to is really from the directed graph to the really is causal network. That means it's how you can break this Markov equivalent structure. That's essentially what that means. So mathematics by the data itself, you cannot distinguish that. Then what other information do you need to break that structure? Then it's from then you have maybe depend on what study you need. Generally, what we study is can we inject some other information that generally called genetics. So how to generate the genetics is this F2 cross. So this one it can be is come from the collaboration with it's Jake Lucis at UCLA, or it's Mark and it's Alan at Wisconsin. Then generally have two different string that either is the diabetes or obesity string, or it's then it's suspect and resistant. Then you cross them together, then get F1. Then you call them again, get F2, then we get really it's a diverse. So then if you look at each of its chromosome, you get all this mosaic. So then from this mosaic, then you can see which one as each is the locus. This one correlate with your tree. Then your tree can be is a clinical tree that's either diabetes or obesity, or we're studying is now people studying is gene expression. Then you depend which tissue you gene expression profile them, and then you study is the genotype. You study is the QTL. When you have this QTL, then it's can merge with the data to construct a network. So before there's everything is from here to here, but now you can get something is from it's a genetics branch coming. So then we hope that genetics will help you to distinguish few of the causal link. So this one is a 95 paper. Generally, what they call is the genetic causality. In general, what I mean, your assumption is everything change is if you have a genetic change, it's on DNA level, it's triggers some change either in the it's a transcription level or it's a protein level, but then all this change then is drive to phenotype change. So you know there's no it's the mRNA or protein can change the genotype. The information can only flow one direction, not the other. So if I can using this one as the linkage, then you can see whether this one is a causal. Then you can test whether it's a gene causal is the phenotype or phenotype causal gene, as long as it has a linker here. Then generally what we call is a test the causality is a causal, reactive, or maybe they're independent. So this one is very, very simple. It's a Bayesian network. You can see the model selection. But only difference is this one is the node can only flow, information can flow out, there's no flow in. So that's the basic form of this causality. Then from here, we have this is association. You end up this best model, but Markov equivalent. Then if we know this one is cis-regulated, so have this one is have a genetic mutation, regulate is the gene function or gene expression, and then this one go to the others. Then all the others cannot regulate the gene with a genetic or that mutation. Then information can only flow one direction, like this one. The only can flow this direction. Then this model with the biology, they're not equivalent anymore, because all the other is structure. So this one. So it's this one and this one based on this edge biological is not possible. So there's the Markov equivalent. End up you can select one is the structure among this Markov equivalent structure based on the biology data. So end up only have one is a Markov equivalent structure is possible. So from there, then if you only have one possible structure, then it get really it's truly it's a causal structure rather than just statistical or it's a computer science causal, but this one is really a biological causal. So that general is we have is the genetics. Then we can go back to is you have if you have either two form. If you have a cis regulation, genetics regulate this one. You have no exactly is from air to here to there. But also there are if you have no is the direct is a cis regulation, then it's more is a causality. You know this one regulate this one, but there's everything there's a prediction. They have it's a confidence will have it's a probability make error. How to capture this error or confident into this model. So you can it's generally how to estimate the confidence. There's several ways. That one is it's a very simple way, just using bootstrapping, or the other way is more using its full probability model to estimate all this causal, what's the confidence of this causal is a probability. Then you can using this as a prior into is a Bayesian network. Say this link is it occurred a lot more by chance, or is this one is likely to happen if they're more likely independent. Then we see this one is likely is if they have any one or the other edge is the chance is very very small. So if you can capture this either causal or independent relationship, then you can it's a complete feeling that it large is when you have a decomposed model, then you have a probability and make one structure is one structure is more likely to happen than the others. So basically, what it does is when you have a genetics, just give you is one from the directed graph to give you some sense as a causal. It's not pure directed graph. That's more like it's a causal. So then question is, yeah, maybe it help you is some is order some is a edge, but how much improvement in general if you integrate genetics, is that improve a lot, or is just marginal, or pure give you is edge? So how we can estimate the quality is the improvement or no improvement on the genetic data. So to answer that, you can do experiment to do that, or you can do a cheaper way to simulate. So we start with let's say this one is apto cross. Can you just rather than take 2 years, 3 years, I don't know how much time Mark is spent. So you can construct another one to replicate, or you can see I can take maybe it's a few days or a few months. It's rather than get experiment data, we simulate across. So you simulate what's QTL effect, then based on its QTL effect or genetic map, then you can simulate tree and simulate the genotype, and then you can just map the QTL. At the same time, you can this value is similar head node, and you give you a known structure. Then you can simulate all the node based on the structure. Then based on this information, is this node value that's essentially similar like a gene expression data, and it's the QTL with genetic data. Then you can put them together. Then you can see whether I only use this is node value, it's the gene expression data, no genetics work, and then put them together. See how much improvement you can get because you know what the true underlying structure. So if you construct structure, how likely it's how similar they are to the underlying structure. So then you can it's vary a lot of different things. Vary the correlation structure, vary number of sample. You can also vary the structure. But generally, this one is one set of data, meaning it's we vary the number of sample, and at each number of sample we see it's that integrate its genetics help you. It's not only a directionality, but how in general it's a quality. So we can see that because we know the true underlying structure, so whether we can see at using different sample risk drug network, is capture all these the link. Well now, so this one is a recall. So ideally you want to get recall 100% capture all the link, but not only capture all link, but really have its precision. We not just a random pick up all the node, all the link together. That definitely get 100%, but the error rate is high. So ideally with the have precision is high and recall rate high. So perfect structure is here. We capture all the link and only the link in the structure. So then we can compare or see whether it's goes to that direction or not. So this one number of sample and so this dashed line is without genetic information used, and this one simple is add genetic prior. Then we can see definitely it's improved. So as long as the same recall, you get higher precision, will get same precision, you get it's a larger recall. So generally we can see, but on the other way, you can see what how much improvement is purely depend on number of sample. So one see at the large number of sample, we can see these two curves actually is very close to each other, but it's a lower number of sample. This one is gap is larger. What it means is at the lower number of sample that the genetics give you is larger. It's improvement. In another sense, in experiment design, if you want to simultaneously capture all this data, the best value with the gain from the generate all the data is the sample size is small. So when you have a sample size large, then most of the information is redundant. So that's why it's a lot of it's a mouse cross that we have. It's a sample size around it's a 200 or 300. That one thing is we know at this time this one is all the investment will give you the largest return. Yeah.
Did you simulate with noisy genetic priors, or were they perfect genetic priors based on the simulation?
The noise is come from here. So even though you have a perfect genetics, but the QTL effect can be strong or yeah. So that yeah, in that sense that it's a QTL effect. Yeah.
I was wondering whether you have a sense of if you have a small enough sample size that including a genetic prior would be useful. Would it be better to include include as many QTLs as you can? Is it better to have like a strict threshold or a less strict threshold on what you call a QTL that goes into your genetic prior? Would it be better to have a noisier prior because there's more good information, or a much stricter?
Yeah, that's a good question. I think there's always they have a trade-off. Yeah, they have it's adding it's whatever prior actually you potentially add noise. So yeah, generally we're using that it's a high confidence QTL to. So generally with whatever is past the genome-wide threshold, then we use that. Yeah.
Is that sample size dependence different for humans in outbred population?
Good question. Yes. So here I want to show that what that means is actually we talk about human data or mouse data. There's major differences. You have it's a control environment a mouse that noise is lower, and human generally have uncontrolled variation. There's noise high. In general, a true correlation structure is weaker. That's really it depends on sample size. What you need to really is capture that relationship. That in general you have human, then number of sample required to get true it's a good quality of network. Number of sample size is required is larger.
1,000?
No, that. So in general, like say we have the yeast that lotus is better than the mouse. We only have 100 is a sample, that's enough. And the general for mouse, it's around the 200, so 150 or 250, that's good. But the human, that it's okay. But in general, we get if below 100, we'll not even try. But 200, yeah, 300, that's a good start. So before this one is the simulation is we simulate ourselves that everything is start with the Bayesian network, and then we can simulate genetics. But the biology that not really is that's not really a Bayesian network. And so this one data come from is the what is the dream is competition that. I don't know what the truly structure is, and they only know is that they have a genetic regulation and there's a feedback control. And can we still capture all these relationship? Yeah, so it's possible. Then really, this one is goes step a little bit further than it have is all the nodes together is not in Bayesian network. Not only have its node represent gene or gene expression, but also have node represent its genetics. So it's a locus. So you can see some of the link is cis regulation. You can see direction from here to here. But in general, it's the genetics only is on the top layer. So you can go from here to here. But also some of node they have under not only under cis regulation but also under trans regulation. So this one is a little bit more complicated and also have feedback control. So if you compare their true network, it's interesting thing is definitely that relate to your question that really not have a human mouse, but really is end up condition is whether you have a weak signal or strong signal, and also sample size. So when you have a weak signal, you have a number size is small. That this red is include is genetics as a node. So either you can construct using only gene expression part, or you can construct network with the genetics plus gene expression. So then compare the truly its underlying structure. If you have a genetic information used, this is our C curve. This one is similar. Here is perfect. So you can see that generally you have the genetic effect will include genetic as a prior. You get a better quality than without prior. So this one is a different structure. They have tons of simulation. And when you have sample size is larger, then the improvement generally is smaller than the small sample size. But when you have really strong signal, then the information you gain from the genetics actually gets small. Or in the other sense is that the prior information, whenever you make an assumption, you always make some error. So there's no perfect assumption. There always you get some noise. So in some sense, you can capture that your network is even worse than without genetic prior. So this one really is a trade-off. So then his question is before is we call it the Bayesian network. There's really is a causal structure, but why you have is a number of sample size is larger, you don't get much improvement. But essentially give you the same as a causal structure. That end up is the Bayesian network. So if we enumerate all this structure, if you can look at here, this one is a different structure. Like say this red is a causal node, this one blue, this one yellow. So this one is meaning is there's one regulator regulate the other two, but this structure is different. So this one we call this one is a divergent structure, right? This one is convergent structure. We specifically call it V structure. what end up is that everything, this structure, there are several, is Markov equivalent structure, but this structure, there's no Markov equivalent. So anything, if you can is construct this network, end up this configuration, this one is truly causal. But if you compare, then you find it's different. This one is really have two parents. If you consider how many parameters you need to estimate in this simple form, let's say this one, everything has 3 states, right? This one you have need is it's 9 parameters. This one 9, so 18. This one is either 3 by 3, then it's need 27. So generally, to get this form, you need more parameter to estimate. That essentially, you need more sample to get proper form because this is complex. All this, when we do a model selection, is penalize complex structure. So if you have a large number of sample, you can sum of structure is end up this form, then it's triggered on a lot of things. It will be end up is it's a log in the causal form, because if this one is fixed, then some other potential get into this one is also fixed because it's a direct acidic graph requirement. So ideally, if you have a large number of sample, and here that we capture is is a nonlinear form, then you can end up of this structure. But if everything is linear, you still have a problem. So ideally, that we need a large number of sample, and ideally is some is interaction. Then you can really unique identify this one. So one is simple. You can for test your hypothesis is based on simulation, but in real data is that actually is the Bayesian network help or not, or it's the genetic data help or not. So there you can do some experiment to test. So you can make some prediction. Then you do experimental test. It generates experimental signature perturb this gene, and then you can go to whatever data you have to predict what the downstream the gene regulated by this Hsd1lbl. So if it's just pure based on correlation, whatever it may be some cutoff, then see predict what the potential is a response gene. Then compare the experimental gene, the only 10% actually is overlap. In using it's a Bayesian network without genetics, definitely you spend it's hours of a day get it's a Bayesian network. It's good thing is improved than simple correlation. But when you have a genetics come in, and then you compare the structure, the predict the response, then overlap is much higher. So at least this form, the symbol is more complex structure, more complicated model. Definitely is a little bit better than the simple correlation, and the genetic also is improved with structure. So we have is not only is the genetics data. There are a lot of other data with this universe with more is they want using the Bayesian network as a general framework. Can we integrate all this knowledge or this high dimension data? We already talked about the genetics data, how to integrate genetics data with the microarray data, but also a lot of other is the polyomic data or genomic data, how we do integrate that. But a lot of things is not trivial. So we now say it's put information together, it's magic thing happened. But if you put two things together, it's more likely to be it's a noise that going to be dilute your signal rather than enhance the signal. Then it's chance if you know there's some information, the question is how you find it's useful information. So here, like a protein-protein interaction, then we can see all these possible pair linked together. And the question is, are they likely to be is correlated in gene pattern space? So this red line, that's all the pair, that's a possible gene pair correlation, you can see that it's most likely that they're not correlated, but there's something is a few chances correlated. But if you try to find all the gene, it's a protein-protein interaction or some it's a relationship in the literature, this black line is a little bit better than the red line. So definitely have information, but still have a majority of them are noise. Then how you can find that the information is this one is generally we construct the networks pure based on gene expression, and so we can see generally the correlation is go to higher, but also answer your question that actually will capture a lot of things they don't correlate at all. So this one mainly is capture the interaction rather than straight regulation. But if you it's kind of intersect with this one with it's the Bayesian network and the literature network only had the yellow line. We see this yellow line is much better than the black line. So goal is how we can capture of this useful information. So in the protein-protein interaction, we know there's a lot of noise. That's one thing, and a lot of things is context specific or it's a physiological condition. And on the other hand, the data is incomplete. So if you want to figure out the noise, that means we not trust of this one single edge, but if you have collateral information, see this all these three or four nodes, they all interact together. We know this one is trustable, so every edge is reliable. But on the other hand, this one is incomplete. So you have to go through it's a partial clean rather than because some of the information is missing. So this one is mainly Bing's work. Then he from this is information how you can find the best is the partial click from the information. If we can derive that partial click, then we can show that it's the best information or best is the if it's the protein-protein interaction we want to get. So like this one, that if you have all these possible pairs and it's all the protein-protein interaction, then you can have definitely have information, but you still have a large a peak with the non-information. But if you have say a derived click or partial click, and we can see that the information peak got higher and the random peak gets lower. So that means definitely we get its information, even though we didn't use the gene expression data at all. So that's pure based on the protein-protein interaction. We get is truly information out of that. Then it's question like we have protein-protein interaction and gene expression. So if we know in this case there are a lot of database give you what is the transcription, what potential is target, then question is are they really in your specific biological condition? Are these the transcription active or not, or whether this form is functional or not? Then we can simple test is if assume this one is active and simultaneously regulate its downstream gene, then this downstream gene should be correlated with each other. So if this downstream gene is not correlated with each other, then we can infer back this one is the transcription is not active. So if not active, we're not going to model it. Similar to the structure, then we have either so we capture this is the potential transcription structure or protein-protein is the interaction is the complex or click. But then question is are they really active in your the specific data set? Then we can see whether that correlation among them is above the random. So if we say this one is everything they're functional, then we can construct a prior. Then this transcription factor regulate gene, and also this one may called scale free. That means if have if the downstream target, if there are more downstream target, actually the make a whole structure is more likely. So not a single edge, but the whole that the structure, the whole structure simultaneous make its prior is stronger. So then is we can test to see whether this Hopper now. So we have this one is there are already some is the data East data that's the one thing good thing is that not only have gene expression is the genotype data, but the public information, all these protein reaction and transcription factor is well annotated or well characterized in the East, so then we can is using this one as a prior. See when we include all this information, are we doing better or is it similar, or which one give you the best is improvement? So we can construct multiple different ways. Prior just using pure gene expression data, or only is gene expression plus genetic data, or it's using everything you can find, put them together. Hopefully not just inject noise, but improve. So then we can compare this network with all these knockout data. See, one knockout have knockout is a signature. Are these signature is overlap your network? Are they overlap better? Or how many of these knockout overlap? So we test about 300 of these knockout data. Then about half of them is overlap. There is the response signature overlap. This our comprehensive is network, but the other one is lower. Then also we can compare it's similar goal term or transcription factor is chip data. So you can see generally when you have this comprehensive prior is overlap your data, it's existing data better. But this one definitely is a retrospective. Then you can see some of the data may be contaminated, but in general form you can still argue. But definitely that's true. The only way to see that anything is power is whether it's prospective validation. You have network and predict which one is the regulator, what's the response. Then you go to generate the experiment data to see whether that experiment data is overlap or not. So we can identify if this one is a key regulator, and we know what the downstream is the regulation. Then we can see if we perturb this one and overlap the signature, are they overlap or not? Then we can see that the significant reach. And here also that we predict this one is the key regulator. Then we perturb then the signature. We see is the overlap. It's enriched in this local structure. So generally is good, but what we want to find is a little bit beyond. To have a keep going. So depend on what we want to find. So here we know, okay, this one is the key regulator. We generate that it's knockout signature overlap. So this one is with perturb gene. Anything this the red is a signature, and also have this red edge. You can see that actually they all have this one is transcription factor. All these nodes have a transcription binding site of this one. So your hypothesis is that this one regulate downstream gene goes through this transcription factor. So we can either look at signature overlap or it's a transcription binding site overlap. They all end up here, and they overlap each other. So that support your hypothesis. But if you look at data, actually this one, the dynamic range from is 4 minus 4 to 4. So you can see that the significant change, and this one is change overlap is the genotype. You know this one, so it's the genotype regulates gene expression, then trigger downstream. But look at transcription factor, the gene expression. This one is 0.6. This one is 4. So essentially, there's no variation, transcription variation of this transcription factor. Then you get stuck. So you hypothesis everything goes through the transcription factor, but transcription factor doesn't change. So what could be happened? Maybe that I think it's the last talk I talked about the missing information. What could be missing is something is regulation. It's not the direct transcription regulation, but goes to some other form. Maybe it goes to a protein. They have a protein phosphorylation state difference, or maybe some is a metabolite difference. So we compare it with polyomic data. There's no information support. So we say maybe that is metabolite data is regulation. So we systematically generate metabolomic data, see whether we can integrate all those information, answer our it's a mechanism question. So here, before we have everything gene expression, genotype, and property data. Now we generate polyomic data. Sorry, not polyomic, is metabolomic data. So we measure all these small metabolites, see what the abundance, whether they're correlated. Then we can integrate everything into this network. Okay. So the first thing is you can see that similar to gene expression, all these metabolite abundant is regulated by the genetics. So we have it's a parental node that this metabolite to isopropylmylate, their abundance is different, and also in the F2 cross, if that specific allele, you can separate the group whether that the segregant capture is carried one of the parent allele, there is abundance is different. So definitely there's is a genetic signal there. And then the question we really is talk about gene expression, or genetics and transcription, polymerase action. But then there's a large information that's a biochemistry pathway we haven't touched. Here is that we capture all this information. We can know what's the metabolite, what's the enzyme. Then one way or the other, depend they're in CAC pathway. Then we can see how likely to be it's linked together. It depends on their distance. If they're one step away or two steps away, if they're really one step away, you get more chance there is related in the Bayesian network. So if we capture that information, then we can construct its network. But here it's the one is a specific, it's a pathway. This one is leucine is a biosynthesis pathway. So here is the intermediate metabolite to isopropylmylate, and we can see that metabolite is abundance is regulated by a loci here. And here is the enzyme in this pathway, this leucine 2, and the gene expression is here, and this one is self-regulated. Then you can also calculate causality, but in general, this one is the cis regulation, it regulates itself, then this one is regulate this one. So you can see this one is causal structure. Then if you look at everything is together, you get metabolite integrate, then you can look at what's the structure, how this one is LU2 regulate all the other one. Actually, it direct goes to this metabolite to isopropylmylate. Then this to isopropylmylate regulate all this gene with is a transcription binding site of this of LU3. Then you can go through the question how this is the transcription regulated. So there's generally people know there are two ways. One is the transcription regulation change the abundance, but we know this one is not true here. But also there's another way to regulate is by this is the 2-isopropylmylase. When you're binding it, you're going to activate that transcription activity. So that's exactly what we see here. This one is here is the 2-isopropylmylate is kind of is a surrogate of a transcription activity, then regulate downstream. So based on all this data, then before we have missing link from here is genotype LU2, then it's get downstream gene. We don't know what happened. Only thing we know is LU3 is a transcription don't change. So what other change we don't know. But now here we have a 2-isopropylmalate. We know this one directly regulate the transcription activity rather than its gene expression. Then it regulates downstream. So give you is more if it's diverse data are going to help you is understand the mechanism better. It's not only it's help you construct better network. So there's a lot of other things. I think is yesterday some people asked all the other is a CAG pathway. Are your network is similar to CAG pathway or not? So really that depends. If you have say this one, you have a CAG is a pathway. The sum of the node we have measured. They have it's a metabolite and also have gene. Then we can see that actually they all is fit in the local structure. Even though there are some people that the biochemical is direction, it doesn't mean have the same causal relationship in the it's a Bayesian network. It just say they have some relationship. It's more likely to be it's a causal reactive one way or the other. So there are a lot of things. One thing is exchange. Now thing is that we see is protein is a lot of protein is a metabolite. You see have this one is regulate LU2 that mainly is related to is the protein biosynthesis. Then we see all these metabolite have a peak there, so they're not surprised. But also find another peak here. Several other have a peak. What they are, so why they have some other form regulation. Then we can see then go through downstream what the gene is underlying this locus. Then you have hypothesis what its key regulator, and then you can see when you have a knockout, which one more likely generates a signature, not this one gene expression signature, but metabolite signature overlap. So we hypothesis is one of these is VPS9 that is the traffic is the vessel is protein mainly is traffic. Things into a central is the deposit. That actually what happened is you have is efficiency of this traffic, then is cell storage of this metabolite is different. So that's if this one is sent to storage, go to degradation. If that degradation efficiency change, then also is a protein or amino acid abundant change. So we can see that the local structure, we have gene expression data overlap, and more importantly, we have knockout this metabolite, all this change as we expected. So that's good. And I think this one is at one more dimension because depend on which camp you are, and if you're doing gene expression, you say that the gene expression capture most of biology, but actually proteomic people say no, gene expression that's most of gene expression not going to translate to a protein and have no effect at all. So here actually it's important. It's a biological find that gene expression have a perturbation have huge transcription response. But people simultaneously doing the proteomic data, they didn't find any variation in the protein level. So the conclusion is all this transcription is just a buffer effect. Nothing translates to a protein abundant variation. So is that true or not? I think that really relates to which closer to the biological system. I think maybe it's a metabolite even one step closer. Especially this function is a stress response. So we have stress response gene, and we find gene expression change, but no protein change. But if you look at this typical, it's stress response. It's a trihalose. They have it's perfect. It's a peak or genetic regulation at gene expression. Similar here. So this one is maybe it's more diverse regulation, but glycerol also regulated by stress. So if you integrate everything together, you can see this one we propose that the key regulator go to is a stress response transcription regulation. At the end, is triggered all these multiply change. So at least we see this not exactly is a buffer effect. We see that clear is a multiply stress response. Can be is mainly one step. So really is test gene expression. We knock out that the gene all the expression recapitulate what we find in the network. But that one still is say that the change doesn't mean anything. And see, one question is see, if you knock out same gene, not only gene expression change, are they multiply change or not? So we did is multiply profiling, then see what change actually that really is a change as what we expect, but maybe more because all these multiplied actually link back to the other. So this one is network we predict, then it goes through one of this master regulator with the multiplied. So then all these other gene change. So that means multiply here that closely relate to a stress response, but also linked to other is a more general effect. So at least one is a different layer, then you can capture what really is a biological meaningful or not biological meaningful. So give you is more confident the network, but also hypothesis is a mechanism. So there's some other thing. It's a lot of data. We have the cancer. They have copy number variation. It's a microRNA methylation. I don't want to go through all this detail, but in general, each data is want to integrate. It's not really that trivial. Each information you have to study what's the potential mechanism, how to get information out of that rather than put everything together, potential diluted signal. So here is the copy number variation. Then you can see what's the potential, what the cis regulation of this one, or what potential is more trans likely to be cis regulation than the others. So you can just formally integrate that. Then you can test whether it's integrate this is copy number variation improve the network now. Then you can test all the overlap, or you can see which one. This one more specific. Say this one have a lot of is a copy number variation in a large copy number variation block. That because mainly is so someone which one more likely to be is a key is a regulator has key signal, or which one is have a more likely to be is passenger is just a station some is key regulator. So then you can test what all these one that is a being and he's supposed to trend is work. So you can test see whether one get all this information integrate is significant. It's enhance your signal to identify what's the true is the signal in this CMV block. So I see just the end here and so say this one a lot of things is a collaboration with a large team, and we have people different people at Mount Sinai, and have is people collaborate is UCLA and University Wisconsin, and so have a lot of East work is at Merck or is UW or Berkeley or Princeton, and last one I've sent to all these people is to support my work. Thank you.